Welcome to EPG Pathshala. In today's module, we are going to discuss about radiation budget of the Earth. Earth's primary energy source is the solar energy, which is considered as one of the fundamental energy of nature, which maintain the dynamics of energy flow for the natural ecosystem services. Every entity of the natural world radiates and absorbs electromagnetic radiation. As photon flux from the sun, which is known as insolation, that enters into the Earth's atmosphere, it interacts with atmospheric aerosols, cloud particles and other atmospheric molecules. Thereafter, the residual resultant fractions are redistributed within the Earth's atmospheric system. The stratified layers of the Earth's atmosphere regulate net energy dynamics in terms of maintaining a thermodynamic equilibrium at any particular location over an extended period of time. Scientists refer this process as global radiation budget that is primarily based on the law of energy conservation. The main source of incoming short-wave radiation on the Earth's surface is the sun. The amount of radiation that is received depends on solar altitude and the transmissivity of the atmosphere. In the absence of clouds, a major fraction of incoming short-wave solar radiation reaches the surface and part of it is reflected back into outer space. The rest portion gets absorbed by the Earth's surface. The Earth subsequently emits a fraction of this absorbed energy as infrared radiation. Energy exchange processes between the Earth's surface and the atmosphere entails warming of the atmosphere close to the Earth's surface and also provides energy to drive the general circulation within the atmosphere. The net absorbed radiative energy in the Earth atmospheric system is transformed into non-radiative forms that get partitioned to heat up the air, ground and provides the energy to hasten evaporation. In particular, the Earth's radiation budget determines the Earth's climate regimes, oceanic circulation pattern and dynamics of hydrological cycle. Meteorologists often consider this entire process as the possible indicator for the climate change. Therefore, it is highly essential to quantify the basic components of Earth's radiation budget towards the effective monitoring and prediction of the major atmospheric phenomenon in the climate change studies. So, in this module, we will be discussing about the concept of radiation energy and energy balance, the incoming and outgoing radiation, the energy components, their spatio-temporal variability on the Earth, also the important physical laws, terminologies and units related to energy transfer through the atmosphere. First, we will see the physical laws that govern the radiative energy transfer. Energy conservation law. When radiation falls on any surface, three possible interactions are likely to occur, that is absorption, reflection and transmission. So, according to the law of energy conservation, Q is equal to QA plus QR plus QT, where Q is the total energy of the incident radiation, QA is the energy absorbed, QR is the energy reflected and QT is the energy transmitted. Therefore, QA by Q plus QR by Q plus QT by Q is equal to 1, or we can say alpha plus beta plus T is equal to 1, where alpha is the absorption power, beta is the reflection power and T is the transmission power. The second law is the Planck's spectral distribution law. This law describes the spectral distribution of emitted radiation as a function of wavelength and physical or kinetic temperature of the black body surface, and it is expressed as B lambda is equal to S lambda T, which is equal to 2 pi hc square by lambda 5 multiplied by 1 by e to the power ch by lambda kt minus 1, which is equal to c1 by lambda 5 into 1 by ec2 by lambda t minus 1, where B lambda is the Planck function derived using the Boltzmann statistics. S lambda t is the spectral emittance, which is expressed as watt per meter square per micrometer per steradian. Lambda is the wavelength of the radiation and the unit is meter. H is the Planck's constant, which is equal to 6.626 into 10 to the power minus 34 joule per second. H is the Planck's constant, which is equal to 6.626 multiplied by 10 to the power minus 34 joule second. T is the absolute temperature of the radiator surface and it is given, or the unit is the Kelvin. C is the velocity of light, which is equal to 2.9979 multiplied by 10 to the power 8, or you can say 3 into 10 to the power 8 meter per second. K is the Boltzmann constant and it is equal to 1.38 multiplied by 10 to the power minus 23 watt second per Kelvin. C1 is equal to 2 lambda Hc square, which is equal to 3.74 multiplied by 10 to the power minus 16 watt per meter square. C2 is equal to Ch by K, which is equal to 0.0144 millikelvin. Wien's radiation law. In ultraviolet, visible and near infrared region, which are short wavelength with high frequency, preferably the lambda is less than 10 to the power minus 3 centimeter. Short wavelength with high frequency, preferably lambda is less than 10 to the power minus 3 centimeter. The exponent factor in the Planck's spectral distribution law becomes large. Therefore, the constant factor may be ignored in the denominator sector and is expressed as B lambda is equal to C1 by lambda 5 multiplied by e to the power minus C2 by lambda t. The expression on the energy distribution pattern in blackbody spectrum is called Wien's radiation law. In this Wien region, lambda, which is less than 10 to the power minus 3 centimeter, the Planck function bears highly nonlinear relation with the atmospheric temperature. The next one is the Rayleigh-Jeans radiation law. At terrestrial temperature T, for long wave spectrum with low frequency of the electromagnetic radiation, which is in the microwave region, that is lambda, which is greater than 0.5 centimeter, the exponent factor of Planck's spectral distribution expression becomes small, and hence the exponential approximation may be expressed as e to the power C2 by lambda t is equal to 1 plus C2 by lambda t. Therefore, following the asymptotic expansion of Planck's spectral distribution law, the expression becomes B lambda is equal to C1t by C2 lambda to the power 4. In atmospheric physics, this expression is called Rayleigh-Jeans law of radiation, and the spectral region where lambda is greater than 0.5 centimeter is called the Rayleigh-Jeans region, where the Planck function is linear to the temperature T. The next one is the Stefan-Boltzmann law. The Planck spectral distribution law confirmed that the blackbody radiant intensity increases with the absolute temperature and the wavelength of the maximum intensity decreases with increasing blackbody temperature. If we integrate the total emittance over the entire electromagnetic spectrum, the emitted blackbody radiant flux density emitted blackbody radiant flux density, that is E lambda, is obtained by integrating the Planck function over the entire wavelength region and is expressed as Stefan-Boltzmann law. E lambda is equal to integrals 0 to lambda. E lambda is equal to integral 0 to infinity s lambda t d lambda, which is equal to 2 pi to the power 5 k to the power 4 divided by 15c square h cube multiplied by 2 to the power 4. And this factor can be expressed as sigma multiplied by t to the power 4, where sigma is equal to 5.67 multiplied by 10 to the power minus 8 watt per meter square Kelvin to the power 4. The above mentioned equation states that the flux density emitted from a black body is proportional to the fourth power of the absolute temperature. And the derived relationship is useful for the analysis of broadband infrared radiative transfer. Now, the emissivity of any black body surface is defined as the ratio of observed monochromatic radiance epsilon lambda is equal to I lambda by B lambda, which is equal to 1. For grey body, the effective or apparent emissivity, that is epsilon, is expressed as the ratio of net radiant flux emitted by any surface, that is E, to that as prescribed or predicted by the Stefan-Boltzmann law. Therefore, epsilon is equal to E by sigma t to the power 4 and E is equal to epsilon sigma t to the power 4 for any grey body. The next one is the Wien's displacement law. Differentiating the Planck's function and setting the derivative equal to 0 at maximum point yields the peak emission wavelength max for a black body at a particular temperature T is defined as Wien's displacement law. In 1893, Wien postulated that particular form of this function from his experimentation on the thermal radiation. From Planck's radiation distribution law, we can see in this figure the dependency of black body radiation on variation in wavelength, lambda and absolute temperature T at thermal equilibrium. The Planck's function demonstrates the spectral distribution pattern, and the Stefan-Boltzmann law predicts the area under the curve, and Wien's displacement law determines the peak, the lambda max for each wavelength. The lambda max is equal to 0.0029 by T, which is equal to 2900 in meter. Lambda max is equal to 0.0029 by T, which is in meter, and if we express that in micrometer, we will get 2900 by T. The Wien's displacement law states that the wavelength of the maximum intensity in the blackbody radiation is inversely proportional to the temperature. The next one is the Kirchhoff's law. This law states the emissivity and absorption as a function of wavelength and temperature for a medium. The law states that if the system or the medium is in thermodynamic equilibrium, that is uniform temperature regime, the absorptivity, that is the alpha of a body, has to equal its emissivity, that is epsilon, at every wavelength for isotropic radiation. That is alpha lambda T is equal to epsilon lambda T. All the above, we have seen different radiation laws, and all these are based on the performance of a black body, that is 100% radiator as well as the perfect steady state emitter. Let's see first the radiation balance concept. The surface radiation budget of the Earth is divided into four major components. Downward short wave radiation, which is denoted as RS with a downward arrow, and reflected short wave radiation, which is denoted by RS with an upward arrow, downward long wave radiation by RL with down arrow, and upward long wave radiation RL with up arrow. The major sub-components of short wave radiation fractions are RS down arrow, that is the downward solar radiation, direct solar radiation, plus diffuse solar radiation, which is also downward. The RS up arrow, that is the reflected short wave radiation, is equal to direct beam solar radiation, which is R direct upward, that is reflected, plus diffuse solar radiation, which is also reflected, which is equal to alpha S, that multiplied by direct beam solar radiation, which is downward arrow, plus diffuse solar radiation downward. It is evident that alpha S is equal to RS up arrow, that is the reflected short wave radiation, divided by RS down arrow, that is the downward short wave radiation, which is known as short wave reflectivity, or it is also known as the albedo. Therefore, the net short wave radiation RNS can be expressed as RNS is equal to RS downward short wave radiation minus the reflected short wave radiation. The net short wave radiation is equal to 1 plus alpha S multiplied by direct beam solar radiation, which is downward solar short wave radiation, plus diffuse solar radiation. Net terrestrial long wave radiation RNL is equal to this downward long wave radiation minus the reflected long wave radiation, where the RL down arrow is the radiation emitted by the atmosphere, which is determined by the air temperature, and RS up RL up arrow. The net terrestrial long wave radiation RNL is equal to RL down arrow minus RL up arrow, where RL down arrow is the radiation emitted by atmosphere and is determined by the air temperature. RL up arrow is the radiation emitted by the Earth's surface, determined by the surface temperature. According to Stefan Boltzmann law, the incoming solar wave radiation, the RL down arrow is determined by apparent sky temperature Ts and sky emissivity epsilon S. Therefore, the equation or the relation may be expressed as RL down arrow is equal to epsilon S sigma Ts to the power 4, where Ts and epsilon S are cumulative impact of all the layers of the atmosphere, depend on cloud cover, humidity, temperature structure, and sigma is the Stefan Boltzmann constant. In similarity, the outgoing long wave radiation, that is the RL up arrow, depends on true surface radiative temperature, that is T0, and surface emissivity, that is epsilon 0, and according to Stefan Boltzmann law, it is expressed as RL up arrow is equal to epsilon 0 sigma T0 to the power 4. Finally, the net available radiant energy at Earth's surface, that is net radiation Rn, is written or is expressed as Rn is equal to RNS plus RNL, which is equal to Rs down arrow minus Rs up arrow plus RL down arrow minus RL up arrow, which is equal to 1 minus alpha Rs direct down plus R diffuse down plus the sigma epsilon S Ts to the power 4 minus epsilon 0 T0 to the power 4. Next one is the energy balance concept. The net available radiative energy, that is Rn, at surface get absorbed on the Earth's surface. The absorbed radiative energy is converted to thermal or heat energy, facilitating the natural transfer of water from the topsoil to the nearby atmosphere. that is the latent heat flux due to evaporation, that is LE, heat the air, that is sensible heat flux, that is represented as capital H, and moves into the ground, that is ground heat flux, which is given by G. The sensible heat flux is responsible for heating the atmosphere from the surface up to about 1000 meters during the day, except for days with strong advection effect. Consequently, the net radiation energy becomes the driver of the land surface energy fluxes, and it is given as Rn is equal to G plus H plus Le plus M. So, in a nutshell, the net radiation Rn, which is actually balanced by G, that is the ground heat flux, H sensible heat flux, and Le latent heat flux, and it is used as plant's metabolic energy M, balancing the photosynthesis and respiration process. It may be ignored as it constitutes less than 1% of the net quantity of the available energy, and therefore it is often neglected. And the sensible heat is defined as the energy that we can sense, that is measured in terms of air temperature. And latent heat Le is the product of the evaporative flux E and the latent heat of vaporization L. Normally the latent heat of vaporization is 2.5 into 10 to the power 6 joule per kilogram. All the energy components in this equation is expressed as flux density unit, that is energy per unit time per unit surface area, that is watt per meter square per second. Under the isothermal condition, Rn is equal to G plus E plus Le. Over 24 hours in a day, the cumulative G is equal to 0, and net assimilation of photosynthates, the net assimilation of photosynthates are very small, those it may be ignored. Therefore, Rn is equal to H plus Le. Rn by L, therefore we'll start good. Therefore, Rn is equal to H plus Le. Rn by Le is equal to H by Le plus 1, which is equal to the acid plus 1, where acid is the Bowen ratio. The land surface features often control the relative partitioning of the net radiation into Le and H components based on available surface moisture. The next one is the dynamics of incoming and outgoing radiation. The sign convention. The components of the radiation and the energy balance equations must accompany either a positive or a negative sign based on the direction of energy transfer. Radiation and energy fluxes are considered as negative to the surface if they transport energy away from the surface, that is removes energy, while downward energy movement towards the earth's surface is considered as positive to the surface. Short wave radiation reaching the ground either from sun or sky is considered as positive, and its reflected fractions are considered as negative to the surface. For long wave radiation, similar sign conventions are used. The sign for the net radiation is as per the resultant sum of the gains and the losses, that is to and from the surface. This figure shows the short wave and long wave radiation balance during day and night time. During daytime, the domination of short wave incoming solar radiation over the outgoing long wave radiation, that is OLR, from Earth's surface results positive Rn availability on the soil surface. In contrast, the absence of Rs downward during night leads to dominance of OLR over incoming long wave radiation that turns Rn into negative and IT. It's clear in these two figures, figure A and B. For any real surface, the heat capacity of the surface objects such as building, plant canopy, etc. play a crucial role for balancing the energy dynamics of the Earth's surface. A finite section of energy is often partitioned into the change in stored energy content of different physical objects. That is delta Qs that present in the atmospheric layer adjacent to the Earth's surface, which is near the boundary layer. Therefore, the energy balance equation becomes Rn is equal to G plus H plus Le plus M plus delta Qs. However, over an open field, the delta Qs fraction is negligible, and the observed variability in radiation and surface energy balance dynamics over 24 hours in a day is displayed in this figure, in these figures. The energy partitioning often experiences a high degree of spatio-temporal variability that determines the mean climate condition and its associated variability. In this figure, the year-round daily average solar radiation intercepted at the top of the Earth's atmosphere across different latitudes is displayed. Sun, the major energy source of the Earth. In this figure shows the radiation budget of the Earth, especially the short wave radiation. The most important and widely accepted principle of climate science relies on the fact that solar energy is the main source of energy for Earth's climate system that control the net energy budgeting and the hydrological cycle. The energy is generated from the fusion reaction with the conversion of 4 hydrogen atoms into single helium atom in the core portion of the sun that results in minute reduction of the sun's mass. The solar radiation is comprised of ultraviolet 5%, ultraviolet radiation, visible radiation 40% and infrared radiation 55% regime of electromagnetic radiation. The upper air ozone layer absorbs radiation with less than 0.29 micrometer wavelength, thus protects the life form on earth from the detrimental effect of harmful cosmic and UV rays. If we consider the total shortwave radiation received at the top of the atmosphere as 100%, then while passing through the atmosphere under clear sky condition, around 35% are reflected back to space. Cloud droplets reflect 27%, atmospheric gas molecule reflects 6% and snow or ice covered areas of the earth reflects 2%, majorly contributes in the shortwave scattering in the space. The remaining 65% get absorbed by the earth atmosphere system, 14% by earth's atmosphere and 51% by the earth's surface. So you have seen scattering and absorption and the reflection of the shortwave radiation while passing the radiation from the sun to the earth. Now we will see the radiation budget of the earth with respect to long wave. As 35% of the total insolation is reflected back as albedo, the balance of long wave radiation accounts for the remaining 65% of short wave radiation. And for long wave radiation, the earth's surface radiates back 51% of long wave terrestrial radiation, out of which 17% are radiated to space directly and remaining 34% are absorbed by the atmosphere, 6% directly by the atmosphere, 9% through convection and turbulence and 19% through latent heat of condensation. The daytime insolation is the major source for rest 15% of long wave radiation. Finally, the 48% of the terrestrial long wave radiation gets absorbed by the atmosphere. That is 14% from insolation and 34% from terrestrial radiation is absorbed by the atmosphere. That is also radiated back into the space. Thus, the total radiation returning from the earth and the atmosphere is 17 plus 48%, that is 65%. That balance the net 65% short wave radiation received from the sun. It is clear from this figure. The cloud cover often reduces the earth's surface energy availability from the solar radiation. The clouds and the earth's radiant energy system (CIRRUS) installed on aboard NASA's Aqua and Terra satellites are used for the quantification of the reflected shortwave and emitted long-wave radiation, aiming to determine the total radiation budget of the earth. The amount of radiation received on earth's surface is often affected by the nature of the surface, that is reflectivity of the surface, incident sun angle, the nature of output from the sun and cyclic seasonal variation of the earth's orbit. Now we will see what are the factors affecting the global radiation balance. The first factor is Earth's rotation. Earth's rotation causes daily variation in net radiation. During daytime, the net radiation is positive, while during night time it becomes negative because of no incoming shortwave radiation. The second factor is the Earth-Sun geometry. It causes annual variations in net radiation, thereby affects global radiation balance. During winter, the amount of incoming shortwave radiation received is less, which leads to less net radiation, and vice versa happens during the summer. And the third factor is the latitude. Equator receives more incoming shortwave radiation, which leads to more net radiation than near poles. The fourth factor is altitude. With increase in altitude, there is less atmospheric reflection, scattering or absorption, which leads to more incoming shortwave radiation received at the surface as well as less incoming long wave radiation. This leads to more positive net radiation during day than at sea level, while during the night it becomes more negative than at sea level. And the fifth factor is surface color. Darker the surface has lower albedo, which leads to lower shortwave radiation and higher net radiation. The sixth factor is the cloud, dust and the pollution factor. Clouds, dust and pollutants absorb the shortwave radiation and long-wave radiation and have direct radiative forcing, which varies between -0.2 to -1.1 watt per meter square. Under cloudy skies, daytime the net radiation at surface is less positive than clear skies, while it is less negative at night time, as clouds act as barrier to the long wave radiation and it re-radiates back to Earth's surface. And the last factor is the meridional heat transport. Net radiation is surplus at low latitudes, which is less than 40 degree north or south, and deficit at high latitude, which is more than 40 degree north or south. Energy is transported from the surplus to the deficit region, that is poleward transport, by ocean currents, that is around 1/3, warm cold winds, sensible heat, it is also 1/3, and moisture in air, which is latent heat, by 1/3. Thus, it prevents overheating at low latitude and overcooling at high latitude. This is known as meridional heat transport. This figure shows the meridional heat transport, and the figure which is on the right side shows the spatial variability in global annual radiation budget. So, to conclude, we have seen the important physical laws governing radiative heat transfer. We have also seen the radiation balance and the energy balance, incoming and outgoing radiation, the energy components, their spatio-temporal variability on the earth, and the factors influencing the earth radiation's budget. The global energy balance approach encompasses the delicate budgeting, providing the information on the role of positional influence, vertical structure of the temperature, and energy profile of the atmosphere to maintain the radiative equilibrium between atmosphere and Earth's surface. It explains the natural greenhouse effect and provides the skeleton for numerical models formulation based on the natural feedback system that aim to improve understanding of ecosystem energy exchange processes. The near surface radiation balance of Earth is useful in the fields of hygrometeorology and climatology. It also helps to determine the climate of any region, the determination of the surface radiative properties like albedo, emissivity, etc. helps to determine the net radiation as the input component of the surface energy budget, also to determine the apparent surface temperature from the space, also to study the radiative cooling or warming processes of the planetary boundary layer, and also to parameterize the surface heat fluxes to soil and air in terms of net radiation. Thank you.